Wait a moment. I think this is too early, right? Okay. Give me a moment just to change this. Is it from here? Yes. 3 hours, 2 hours is fine. Okay. All right. Okay. And I'm also grateful to the NewcompStar action that is also taking care of part of the costs for my participation here. So let me just mention what this cost action actually is. This is a grant for networking in Europe that Luciano with Pierre Pizzochero successfully got a few months ago, and it actually started. And what it does is to enable networking between groups in more than 28 countries throughout Europe. You can see a list of the countries here. So practically all of Europe is participating to this, but not only Europe, also Israel, and there are also a number of participating countries that are in collaboration with people in the European Union. So there is a main site in Frankfurt set up by Luciano that describes the themes in which this network concentrates. There are various working groups, 3 working groups, one on astrophysics, which is led by José Pons, one in nuclear physics, which is led by Jérôme Margueron, and one in gravitational physics, which is led by Ian Jones. And then there are also people who try to make sure that these 3 different working groups are not isolated by that they talk to each other. These are the synergy agents, Pavel Hensel, Valeria Ferrari, and Michaela Ortel. And here again you see the working group leaders and the chairs of the steering committee. So as I said, the main activities are networking activities, and from twice a year there is a call to fund individual travel. So if someone in, let's say in Greece, has a good collaboration with someone in Germany and they want to exchange travel, then they can submit an actual proposal and get this funded. So Luciano, I think you should say a bit more about this.
I think this is more enough.
Okay, okay.
Maybe the only thing is that these travel grants are always running. They are more than 2
I see,
calls.
yeah, more than 2, okay.
Essentially
Okay.
every 3-4 months.
Good. All right, okay.
Would it also pay for US collaborators to visit?
So this is where the complications are. This is really organized so that it's within Europe, but there are possibility of ways around this. So we first have to have a given EOS institution be approved as a partner. Once that's done, then that can happen and you can be supported. So it is possible to do this, but it's a bit more elaborate.
Mm-hmm. All right, so then I can start with the actual talk.
Does it also organize meetings?
Yeah, it organizes conferences and schools. There's been a conference in Florence at the beginning in March, I think, and then there's going to be a school in Barcelona in September. So the website has all of these events.
Mm-hmm. All right, so the topic of the talk is the post-merger oscillations in after a binary neutron star merger, and I have split this talk in 3 parts that roughly correspond to 3 recent publications. Part 1 is understanding the post-merger oscillations. This is based on a publication from 2011 with Andy Bauswein, Kimon Zagouris, who was a student in Thessaloniki, and Thomas Janka. A second part then is how one can start to extract information from potential observations in gravitational waves in this post-merger phase. This is now in press in PhysRevD with Andy and Thomas. And last week we also submitted a new paper to PhysRevD. This is in collaboration with James Clark, who did most of the analysis for this paper, and Laura Cadonati, Thomas, Chris Panko. And here I will only mention how we are trying to set up hybrid waveforms that continue the simulation to longer times. And then James will talk tomorrow and give you the details of what was actually done here. I will not go into this. So part one, yesterday Satya set the stage for this meeting for discussing the phenomenology of the binary neutron star mergers. So it seems that the most likely range of masses for these mergers is in a narrow range, somewhere between 2.7 and 2.8 solar masses. And because of this recent 2 solar mass neutron star, we now expect that the remnant will actually be long-lived. And so this is very positive for trying to detect gravitational waves from the post-merger phase. The remnant is a hypermassive neutron star. It is supported by differential rotation. Later on in its life, if the differential rotation becomes uniform, it may actually collapse to a black hole. And already yesterday we saw this kind of representative cases that there is a in-spiral phase, a very brief merger phase, and then followed by this post-merger ring down. And if you do a Fourier transform of this signal, this is the H plus amplitude, and you get this spectral density as a function of frequency. Then in the simulations we don't actually get much of the in-spiral, but we do get all of the post-merger, and you can clearly see that there are some certain characteristic frequencies that stand out. This is roughly at 40 megaparsec. So for advanced LIGO, this is above the noise. It's not with a high signal-to-noise ratio, but at least it's above the noise. Same here. The other frequency is not. But maybe for ET, maybe much later, there is something could be interesting there. Now, the question is, are these just some random oscillations, or is there something that is organized here? And our understanding is that as soon as the two neutron stars merge, they form a single self-gravitating object that can only oscillate in its normal modes. Even though initially the oscillations are highly nonlinear, it is still a nonlinear extension of these well-known linear oscillation modes. And in particular, we wanted to focus on this triplet of frequencies because we noticed that the distance between these two is roughly the same as the distance between these two. I will show more cases later. The actual simulations were done by Andy Bauswein. Andy has a code that runs very efficiently because it uses SPH and CFC for the spacetime. So it has a much larger time step than a full GR code. And it needs less computational power in order to run the SPH part for the hydrodynamics. So in practice, Andy can run on workstations with, let's say, 12 CPUs. Within a week, he has already a model running. So in this way, he can sample a large number of equations of state and a large number of masses. And the typical outcome of these simulations is that as soon as the two neutron stars merge, you form a transient structure that is a combination of a rotating bar in addition to radial oscillations. And so this combination is practically an m equals 2 oscillation mode and an m equals 0 oscillation mode. And that gives you what you see in the simulations. In order to determine the nature of these peaks after merger, we split the time series into two parts. One part where we did an FFT at pre-merger time. So and actually we split them here at this point. What is this first line? And there you don't see any, at high frequencies, you don't see any trace of oscillations, just a broad spectrum that is a continuation of the inspiral alone. And if you do an FFT of the post-merger part, which is this green line, then you see all these peaks that you also see in the black one, which is the full, the FFT of the full time series. So clearly, these peaks are there and appear only after the two stars merge. And the reason we think that these two peaks are sidebands of a main peak that is the m equals 2 is that we have studied such cases before.
Can you go back?
Yes.
In that plot, I think I probably missed, you got two different curves and they are for two different equations of state, is that?
Oh, this is a single run, one equation of state, one mass, and so if you do the Fourier transform of the whole time series that includes the pre-merger and post-merger phase, it's this black line here.
Right.
Then if you cut the time series in two parts, before merger you get this FFT, the red one.
Before the merger.
Yes.
I
After
need to
merger.
understand that from your simulation point of view. What do you mean? I mean, they're not touching each other
Yes.
at the moment. Okay.
Yes, they're not touching each other.
Okay.
And after they start touching, then you do an FFT of that part, and that's the green one. And that gives you these frequencies that you see also in the full signal.
But that F minus has some contribution that seems to be coming before. That's a log scale, isn't it? That's a log scale.
This is a log scale, yes.
That F minus,
Yes.
where you are, I don't quite know, I mean, because there seems to be a lot of structure there. I wonder whether there's contributions coming even from before.
Well, if you look at the pre-merger spectrum, it's just a smooth fall off.
Yeah, exactly. There is no feature here,
The black
no discrete feature. It's just a fall off here.
The two don't add up, do they?
They don't, and in fact, because this is a time series of a finite width,
What kind of window do you take?
here we have this Hahn window that we
You know
apply.
if, okay, does it cut off the power significantly?
Yeah,
At the edges?
we experimented a lot with windowing and with different kinds of windowing, and also with the time that you start to apply and with a split. This is now a result where we feel that we get the physics out, and it's not something numerical.
I agree, but all I'm saying is that the sum doesn't add up, mainly because of windowing that you have used.
Sure.
It's not a
Yes, yes. Yeah.
coherent addition. I mean,
I agree,
Yeah.
I'm not denying that,
Yeah.
but it somehow has to see that second peak is coming from somewhere, and that it doesn't seem to be produced.
Second, which
What
one?
I mean
again?
is you got the red curve producing a peak, the black one immediately.
Oh, this is actually not the peak.
No,
This is the in spiral comes here,
First peak.
and this is then the first
There
peak.
was a little structure
Yes.
before in the second peak.
Yeah.
That doesn't,
Hmm.
you're saying that it doesn't have to add up, is it? Josephine seems to suggest.
Well,
I thought it must be the window effect. The window is.
yes,
doing something.
we are using windowing, and it does have some effect. So you cannot expect the
You
two.
can use something called a Planck window,
Uh-huh.
which is very smooth. It's a C infinity function,
Okay.
and it kills very little power, and it
Okay.
doesn't add any artifacts. So
Well,
we can talk about
you're
that
sort
later.
of limited by the very small merger time window. I mean, if you want to eliminate finite time effects, you need a long time to window over, and you don't have it if you want to divide precisely in the merger. So there's some inevitable structure that will come out of that.
And the way I understand it also is that here, at this time, you have a very sudden change of phase. Up to here, you have this chirp signal,
Yes, now I've seen it
And-
at
and-
university. Yeah.
and then suddenly there's a change of phase. And here is exactly where we split it. And you want to apply an FFT, so it cannot.
The way I'm thinking about it is that it's like falling, and then there is no dynamics anymore for a little short time. That's the reason
Mhm.
why the amplitude comes down, and then there is oscillation. So
Yes.
that's the way I look at it.
Yeah. Mhm.
And that bounce produces that.
Yeah.
structure.
Okay, so in 2007, when Andrea Passamotti was a postdoc in Thessaloniki, we looked at nonlinear combination frequencies in non-rotating star, and how these translate in the gravitational wave spectrum. And indeed, if you set up in a non-rotating star various oscillation modes, and Andreas had actually a high order perturbation code with which he could add nonlinear effects to that, then in the spectrum one can clearly see such combination frequencies between different modes. So all over the place you have the main linear frequency and then also additional combination frequencies, which are linear sums and differences of the main modes. So motivated by that, we analyzed a large number of cases with different equations of state and different masses, and we looked at the Fourier transform of fluid variables inside the star, so the density integrated in the equatorial plane. And here you can see, for example, the m equals 2 oscillation mode, the quasi-radial m equals 0, and this is their difference and their sum. And now if you compare to the gravitational wave spectrum, you can see the m equals 2 translates here in gravitational waves, the m2 minus 0 translates here in gravitational waves, and there is also a correspondence of the 2 plus 0 frequency. So we call these f2, f minus, and f plus. This is for the Lattimer-Swesty equation of state with equal masses. If you now use an unequal mass case, then in addition to the previous frequencies, you also have the excitation of an m equals 1 oscillation mode, which is actually quite strong in the hydrodynamical variables. And then you also see combination frequencies. For example, the sum of the quasi-radial and the m equals 1 is here. Their difference is here. We also see the m equals 3 mode and various combination frequencies. So practically all of the peaks that one can see in the Fourier transform of the hydrodynamical variables, one can assign a certain combination frequency to them.
So, Nick, the green is the time series after the first vertical dashed line, right?
Yes, yes.
And this FFT is also over that same window after the
Yes.
first.
Right.
Now, have you looked at what happens if you, to your spectral density, if you take away the slice between the two vertical dashed lines?
Yes. Then the amplitude of this f minus goes down.
Mm-hmm.
Its frequency slightly changes, but not dramatically. And the reason is that because this is a nonlinear feature, after the first few cycles, already the amplitude of the oscillations starts to diminish. So their combination, because it's a higher order, it goes down rapidly in amplitude. And also, we should keep in mind that when the two stars merge, they are not yet in full equilibrium. They still evolve and try to become a single star that satisfies the conditions for equilibrium. And so there is still some evolution there. And this evolution in the first couple of cycles gives you a small shift in the frequency.
So, and what happens to the F plus? Does it just do the same as F minus?
The F plus is really difficult. You see there's quite some noise here. So we did not really focus on trying to see in great detail how it changes within a couple of cycles. So we mainly focused on these two.
Because if you go back to the equal mass case, what we have done is, well, very similar to what you've done. We have looked at the spiral only, we've looked at the post-merger only, we looked also at the post-merger, but the slice of the, transient, let's say. And there we see clearly that F1 and F3 disappear essentially after the transient. And most of the power that you see in the full post-merger power spectral density is built in that very little window.
In the first cycles, where it's still highly nonlinear. Yes. But but the interpretation, our interpretation is still that these are the combination frequencies.
Well,
because we see this triplet. If you look at different equations of state and different masses, you always have this triplet. If there was something else here, then in some cases you should see it.
okay.
You should see both the triplet and the other feature.
It's a matter of interpretation. And I don't want to, interrupt your talk. I would say that if the coupling is nonlinear, then the power in the bands should be comparable with the power. Should be less, but comparable with the power in the first peak. And if it is a small nonlinear coupling, then you should still see some bands, but it's much smaller, much smaller amplitude, which is what we see if you take away the first line. So it's a matter of interpretation, what you call it. Whether it's a nonlinear coupling or in this, a transient with a mostly, this two spheres toy model I was thinking about.
Yeah. No, I agree, because quantitatively our simulations show the same thing. Now, how you interpret it, it is a matter of interpretation. This was the unequal mass case. And now to double check that indeed what we see here is we don't put wrong labels on the peaks. Yes, Jocelyn?
Maybe you're about to answer this, but it doesn't seem in the unequal mass case that you have very different structure compared to the equal mass case.
Yeah,
it's contributions, or they're not strong?
The M equals 1 do not radiate strongly. You don't see them here.
Is that just because they're close to equal mass, do you think?
Yes, the variation in mass ratio this is a typical variation that we have in the mass ratio. And up to such variation, the main peaks like F2 and F minus are not sensitive to that. They are characterized by the sum of the two masses, but not so much only to a higher order by the ratio of the two masses.
In your conformal flux simulations, gravitational waves are computed by Cutler-Hall formula, right?
That's true, yes.
So I think if we could see some higher angle gravitation, for example, we see in numerical relativity by psi4, I think there may be some contribution from odd mode oscillations for higher, for example, L equals 3 or M equals 3 mode.
There will be, because you do have, here we only have the M equals 2 extraction. Yes, there are, but because this is a log plot, these are all orders of magnitude smaller than the main feature. And in fact, Luciano's group in their simulation have looked at similar setups, and they confirmed that the frequencies are correct, even though we use the CFC approximation.
So
how does the width of the F2 peak vary with mass difference?
Now, the width of the F2 peak depends here on several factors. In the numerical simulation, it mostly depends on the numerical damping that is there in your code, and on how close you are to the threshold for collapse to a black hole. So if you have a case where you are near the threshold to collapse, then the star starts evolving towards that threshold. So that changing background changes also the frequency and gives you a larger width. If you are far away, what we see here in the damping, initially this damping is because of nonlinear effects, and later there should not be such a strong damping as here. This is caused by numerical finite resolution. In fact, these are plots from 2011. By now, Andy has improved considerably his numerical code, and he can extend this to finite amplitudes to longer times. And so the actual width is not as large as shown here. It is somewhat smaller. On the other hand, now if you are asking what is happening in a real situation, this will radiate in gravitational waves on a time scale of 20, 50 milliseconds. So there, because you lose gravitational waves, you do have a change in the angular momentum. You do change the background. The frequencies are shifting. So there will be definitely a finite width of this because of actual physics. And this is actually our ultimate goal, to try to reach a description of that. That includes the actual timescales. Now, to make sure about which modes we are seeing, we apply an eigenfunction extraction to the data of the numerical simulation. So we do not have an eigenvalue calculation. These are simulations in time, but still we demonstrated some years ago with Apostolatos and Font that you can extract very accurately the eigenfunctions of various oscillation modes. This is for the L equals to F mode in a non-rotating star. This is in a very rapidly rotating, differentially rotating star. And this same technique that we demonstrated there, we applied here in non-axisymmetric oscillations. In the equatorial plane, if you extract the Fourier amplitude and the phase of this at various points in the equatorial plane, and then you compare them, you can clearly draw what the dependence of the eigenfunction should be on location. So you can extract the m equals 0 eigenfunction, the quasi-radial oscillation. The m equals 2 has a very characteristic quadruple pattern. This is m equals 4. So although the code is an SPH code and uses a limited number of particles, still it can describe high-order oscillation modes very accurately. And this is the m equals 1 in m unequal mass case. So to summarize this part of the talk is that by doing eigenfunction extractions and by comparing the frequencies in these spectra, we arrive at the conclusion that we see a main m equals 2 mode and nonlinear combination frequencies with the quasi-radial oscillations. And as a continuation of this, we are now trying to reconstruct the equilibrium structure of this post-merger object. It's not in exact equilibrium, it's in a quasi-equilibrium, but still one can approximately define an equilibrium structure and then do actual eigenvalue calculations in order to confirm with another approach our findings. The second part now is how one can use this in order to infer information about the equation of state. This is Andy's main work, in the last years. So I will summarize it here for you. I first show the final slide, and then I will show how to arrive at this. So the result that got us very excited is that it seems to be possible using observations of the F2 frequency in the post-merger phase, if you have at least two observations at somewhat different mass, it seems to be possible to constrain not only the radius at a certain mass, because this can help you, or maybe not, because some of the equations of state cross right there, and then you don't know which one it is. But at the same time, this method allows us to predict with a certain error bar the mass and radius of the maximum mass non-rotating model. So it could be here or it could be there. And in this case, it is very helpful in distinguishing equations of state. So how can one arrive at this? Andy has used in a previous publication with Janka, Hebler, and Schwank 2 years ago, he used a very large number of equations of state. Some of these are really two-dimensional hot equations of state. Others are cold equations of state that were supplemented by a thermal part. And what he found is that if you plot the F2 frequency, which there it is called F peak. So whenever you see F peak in these plots, in the remaining of the talk, it is the same F2 that I talked about before. If you plot the F peak frequency as a function of the radius of a non-rotating star with 1.6 solar masses. In that case, you get all this data for different equations of state and different masses, but these data are not randomly here placed. But if you now ask, what do you get for 1.2 plus 1.2 solar masses, you get a nice linear relation here. If you go at higher masses, you get another nice linear relation. At different masses, 122, 25 plus 1.5, these are unequal. Well, I did not have a line for this, but okay, the final line is for 1.5 plus 1.5. So the outcome is that the F2 peak that one could observe in gravitational waves can tell you quite accurately what is the radius of a non-rotating star of 1.6 solar masses. All you need to know is what are the masses of the two stars that merge. But this we should know from the in-spiral. Right? So if you make a detection and from the in-spiral you have information on these two masses, then you can go back to this graph, select your line, and measure. If you measure the F2 peak, you get the radius of the non-rotating star at 1.6 with an accuracy of just a few hundred meters.
Question.
Yes.
There'll be an error in the determination of FP.
Sure.
Well, about how much?
Okay. So this is something that actually James will talk about in detail tomorrow. So maybe I should not go into this because
And to what accuracy will the masses be measured?
All right. So this is now a measurement of a determination of radius from the frequency, and then I will talk exactly about how one also can get the mass and to what accuracy.
So if I want to look at how Fp changes with for the same equation of state, what do I have to do to compare a square and a cross which have the same abscissa?
Same equation of state but different masses, we say. Well, here.
Yes, just vertical.
Yeah, just vertically.
Yeah, so this is not very different from what we found as well. That
It's
essentially there is revisit generously with masses as you go to different
Yeah, yeah.
masses, you will see
Right,
different
right.
equation of state.
It's a different cross section. So the results that you have in your recent paper are in full agreement with this. Yes. Okay. So now, for example, if you look in more detail at the case of 1.35 plus 1.35 solar masses, which is the most likely case, indeed, this relation between the F peak and the radius at 1.6 solar masses is very tight. It has a very small spread. And so here, Andy has constructed these empirical relations, and one can divide it in two lines, basically, with very small inaccuracies. But that's not all you can do, because this gives you the radius, as I said before, the radius with some inaccuracy at 1.6. Now, how do you get information about these stars, which you cannot really hope to observe in binary neutron star mergers? For two reasons. First, they are very rare. I mean, the expected masses are somewhere here. And even if it happens, and it will probably collapse very quickly so that before you can even measure it. So, how can one estimate the masses and radii there? All right, wait a moment. Okay, first, let's give a small explanation about this actual correlation between the F peak and the radius. It can be explained because this frequency correlates with the radius of the remnant. The radius of the remnant is proportional to the radius at 1.6 solar masses, as Andy found by looking at his simulation data for a large number of cases.
So how do you define the remnant radius?
This is so you have your remnant, and then if you look at a linear graph of density, where this goes to practically to zero. Okay, in reality, the distribution of density extends to many radii, but it's very small. You have a very low density envelope surrounding this star, but you can define a practical radius where you have, let's say, 98% of the mass enclosed. So this is such a definition here. And now,
What about if it is not axisymmetric? That is, as an M2 component. How do you take
the
it from
component after about 10-15 cycles, the amplitude of this is quite small, so that it's almost axisymmetric.
in some simulations? Because not always the amplitude goes down very rapidly, right? As you said.
For the F2, the amplitude in the fluid, if you go here, where is this? Okay. Here you have a large amplitude in the first several oscillations, but then it decays non-linearly.
You can associate an ellipticity to the star or to the remnant,
Yeah.
which may be what, 10 to the minus 1, 10 to the minus 2?
No, but that depends if it's a function of time. I mean, in some simulation, depending on equation state, we see that for 30 milliseconds, the amplitude is essentially unchanged.
But how large is it?
we
That
can,
matters. Is it, if you associate an ellipticity?
Well, it's whatever is producing the gravitational wave. So
That's correct. So one can get an
Sure.
estimate of what the
From a
difference
simple-
is
Yeah.
in different radii.
but it's of the order 10 to the minus 2 or larger.
Yeah. Which means it doesn't matter much.
Yeah. For the radius determination,
Directions
this is very small, and you can also average over a few cycles, and you have an average radius.
Well, I don't disagree. It's just
Yeah.
that it's
Sure.
an error.
We should
bring
take that in
in
mind.
another error in the definition of
That's correct.
our remnant.
And the remnant is irrelevant,
Right, doesn't this, so you read off F2 from the LIGO or whatever, and then regardless of the EOS, it tells you the radius of a non-rotating star at 1.6 solar mass.
That's true. Yes.
Right?
Yeah. It's an equation of state independent relation.
Right.
Yes. Yes.
And it doesn't depend on the remnant at that point. Once you have F2,
Oh no. The question was about the precise definition of the remnant radius here.
but this doesn't tell you the remnant radius. It tells you the radius of a non-rotating.
But he's claiming that the remnant radius is correlated with the
Yeah,
radius,
yeah.
the 1.6
Yeah.
mass.
In-
So it's a correlation that.
The question is,
In practice, you don't go.
establish that correlation.
You don't go through this. This is just an explanation of why there is such a relation in the first place. Just to understand it better. Okay, and now.
Why is remnant radius correlated to R1.6 and not R1.4 or R1.8?
It is also correlated to other masses.
Why
Yes.
did you pick 1.6? Was the relation tightest?
Exactly. So when you look at the spread of the error for these different relations, you can make similar graphs using here 1.4, 1.8, 2, and the error is minimal at 1.6 if you look at all these cases. Yes.
Is there any physical explanation why that happens? Why the relation is tightest for 1.6?
Essentially, it's because the density regimes are very similar in a 1.6 non-rotating neutron star and in a much more heavier star that is rapidly rotating, potentially rotating. You have essentially the same density regime.
Now, what do you exactly mean by density regimes?
The densities that you find in the remnant and in this non-rotating neutron star. So if you somehow define it, of course, the central density of the remnant evolves in time, but if you somehow define the maximum density, then it's more or less the maximum density that you also find in a 1.6 solar
Yeah.
mass neutron star, which is not rotating.
Yeah, this is what we saw, that the central density of the remnant is somewhat larger than the one of the individual stars. So from 1.35 you go to something like 1.6.
So the density profile is largely set by the angular momentum, or to what extent does the thermal response of the pressure play a role?
The thermal pressure plays a role, but I think not too much, maybe a few percent.
Yeah.
But when we change mass, the relation changes a bit, right?
Yes.
So have you checked that if you plot M frequency, does it make it dimensionless?
Okay. I'm not sure. Andy, have you done something like that?
Right.
Yeah.
All different masses, I mean non-rotating masses. What you find is that depending on the total mass, one non-rotating mass works better than another, which is simply because of this density regimes.
What
And-
I'm saying is different. So if you plot this instead of F frequency, MF,
Yes.
you make a trivial mass scaling, and
Mhm.
in other situations this works.
Mhm.
And you may have a real.
I could imagine that it works also here because, for instance, the 1.2, 1.2 scale with the radius of, I don't remember exactly, maybe 1.4 or so.
Yeah.
So I guess you could find this
Yeah.
Because there
universal behavior. that
That
you
would
want.
be a stronger statement. You don't have to change your diagram every time you want to record
Mhm.
the power.
Yeah.
Then you just use one.
Yeah, that's a very good point. Yeah. Indeed, when you look at frequencies, or at oscillation frequencies, you can find nice scalings. I will show in the third part such a case where if you compare how the frequency looks like in the inertial frame compared to the co-rotating frame. So also here, by using what you said, it may look even better. So that's something still to be done.
Because this is something we were discussing yesterday afternoon. There is a similar plot where you
Mhm.
have F peak versus the compactness, and you
Mhm.
see essentially the fact that you have different relation for different masses, and you see that the scattering doesn't really decrease if you go to Fm rather than just F.
Mhm.
So
Mhm.
you can try yourself, but I
Yeah.
don't think the scattering will disappear.
Yeah.
if you-
Okay, we'll try this. We'll try this in any case. This is helpful suggestion.
So 1.2, 1.2, obviously, if the squares are, if you multiply the mass, they're going to make it even go lower compared to the diamonds. 1.2, 1.5. I think the spread will only increase.
Okay, so Andy will tell us in the afternoon.
Right.
He can quickly rescale the data and then show us another plot, and we'll see.
I'm just saying, looking at the square and looking at the
Sorry? Yes?
square and diamonds, right? So diamonds is larger.
So different.
No, no, the squares and crosses.
Here is the legend for them.
So yeah, square and diamonds.
Go to diamond, go to
is larger
the next
mass.
one.
So
Yes,
if you multiply that mass,
So the frequency.
The slope is that same? I think it's different.
Yeah, the slope is.
No.
These are approximate lines that I drew over the. Yes?
But I think they are different.
For educational reasons. They're not
That's
precise
pretty-
lines.
Lines are different, the slopes are different.
yeah.
So this is a precise line. It's actually two lines of roughly similar slope. And you can construct then graphs like this for other masses also, but this one has the smallest uncertainty. Now, what is the other idea of how to also constrain the mass and radius of the maximum mass model? The idea is that if you plot now the peak frequency as a function of mass, of the total mass of the system that is merging, you can see that in most cases you get almost a linear relationship of the peak frequency compared to the mass.
That's
The-
not, can you explain what exactly you're plotting?
Yeah, so this is the peak frequency that you extract from the post-merger phase, the quadrupole frequency, and this is the mass of the binary. And each line is a different equation of state. Okay.
Is that baryon mass?
These are the gravitational masses. The sum of the gravitational masses when you have them in isolation. So initially these lines are linear, and then only when you approach the threshold to collapse, so each equation of state terminates here, 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 when you have sufficient mass to create a black hole. Okay, and when you are near this threshold, the line changes, the relationship becomes nonlinear. But still, what Andy found by analyzing all these cases is a strategy of how to extract useful information.
But what about lines that are crossing? Are you ignoring them? There are some lines that seem to cross.
Yeah, so the idea is that you may be able to observe two systems with somewhat different masses. One, let's say, at 2.4 and one at 2.6. So you start with these 2 points. And then these 2 points you extrapolate. I show it here. You extrapolate the 2 points. Then you apply a correction because of this bending. But this correction is applied in the same way to all equations of state, independent of which one. And then you have a...
But there could be confusion. Imagine that I have 2 dots. Won't there be a confusion that we don't know on which path they lie?
Yeah, there's going to be some error bars.
There will be error bars, yes. That's why these boxes are quite large, but still useful.
All I'm saying is that
Mhm.
take the 4th and the 5th one there, okay? Okay, those
Yeah,
two.
okay.
Now, if you observe 2 masses and the next 2
Mhm.
points are exactly the same,
Mhm.
and then you don't know which path you are on. They are significantly different. You know what I mean? If you give me your laser pointer, I'll show you.
Yes, okay. Let's see exactly.
Is this the laser pointer?
Sorry, yes.
Which one?
This one, yeah. The triangle.
You start, so you make one measurement here, you don't know which is this.
Yes.
Then you make another measurement here. These are your starting points.
Yes.
And then you want to extrapolate, but you don't know whether you're on this path.
Oh, you don't need to know it. All you need to know is the slope of this. All you need to know.
Yeah.
You have two points and you have a slope.
Yeah, but would
This-
you go like this?
This slope takes you initially.
Yeah, but that could be this.
So
Because I
your
really
final
don't know.
result.
The-
has
the-
that
the-
error bar.
then you have an error bar here.
Ah, okay.
Yes,
You do.
exactly.
Which could be pretty big in some cases.
Well, I will show how much this, because Andy analyzed all these cases. So for these particular equations of state and for additional ones that are not shown here. Initially for these ones, he found that the sequences terminate along these two lines. And so that's how we submitted the paper. And more recently, he got additional equations of state available, so he added those that are filling the gaps between the ones that he already had. And basically what he found is that the termination point is somewhere in this triangle. It's not widespread, it's somewhere there. So all he had to do is to shift a little bit the initial lines, to shift them here. Then you start with two measurements, extrapolate. He has a detailed recipe in the paper how to apply this bending towards the end, and then you find a final estimate for the threshold mass and for the peak frequency.
Now, this threshold mass is computed how? This is not the maximum mass of the non-rotating star, right?
These are the actual remnants. If you increase the mass of the initial
Yes.
two stars, at some point you see them collapsing instead of creating a stable remnant. And so within about 0.05 solar masses, looking at different cases, he could determine what this limit is.
Okay, but this is where word of caution should be made, because determining the threshold to collapse, you really need full GR, and this is where CFC might be not very accurate. What is the precision at which you measure this threshold mass?
Within the CFC approximation, it's 0.05 solar
5%
masses.
solar mass.
Yes,
Yeah.
within the CFC approximation. Now,
This is the reason why you have a large error bar in that very first plot that you showed
Yeah,
for the
yeah.
threshold to collapse.
yes. So Andy wanted to say.
May I add something to this question? How important it is to determine the threshold mass precisely? Actually, it's not really important to determine this threshold mass precisely, because what we actually connect is information of gravitational wave signals of low mass mergers, right? And then you could consider this whole procedure an empirical procedure to connect the gravitational wave signal of these low mass neutron stars to the properties of non-rotating neutron stars. So essentially, it does not really depend on the meaning of this threshold mass.
Well, but you see, this is something you have to take into account when doing your proper error budget. Everything.
No. My point is that I do not need to do this.
Well, but I don't understand. Geometrically, this line can be very, very thick or very thin, according to how well you can determine that.
Yes, exactly.
So that will is something.
This is what matters. This spread is what matters.
What do you mean with that spread is what matters?
So this
But if you consistently apply the same definition and the same way of determining the threshold, what is called here the threshold mass, then what matters is the spread between different equations of state, and not the precise onset of collapse. Because later on, this will be clear, I think, in the next step, that this now empirically determined threshold mass from the simulations. There was another paper last year at PRL, Andy, Thomas Baumgarten, and Thomas Janka, that found that this threshold mass is actually, you can relate it to the maximum mass of a TOV star. And so this relation is determined by the simulations also. So these are empirical relations.
This is where
If you do it in full GR, you just have slightly different k.
Well,
But the methods will still work.
Well, but I'm not sure that other terms will not be important, like mass ratio, like spin of the progenitor. I mean, this is too simple to be good.
So, there will be.
You could do a direct correlation between.
Okay, so here is the challenge.
points and
Here is the
properties
challenge.
Of a spherical star. Yes. So you could do a direct. So this is, in a sense, they're going through some extra steps to try and get physical information, I think.
Mhm.
But in terms of just the mathematical empirical relationship, you could
Mhm.
take just the two low mass frequencies and then correlate that with the maximum mass of a non-rotating star. And the error budget in each of those two pieces is more under control than this threshold mass. But that's all that the relationship that Andy
Exactly,
developed
yeah.
depends on.
You could consider this whole stuff, the whole story with the threshold mass, you could just consider to be a black box. Just to relate the data at low masses to the data of non-rotating events.
Yeah. Some fiducial mass. Yeah. Okay, so now they show that such a relation exists also with high accuracy, and this k actually depends on compactness. And so if you define compactness in terms of the mass and radius of the maximum mass TOV star, then you get this nice relation here between k and that. And you could also define compactness in a different way using the maximum mass of that model, but the radius at 1.6 solar masses. And again, you see a nice relation. So this is then how the determination of the threshold mass takes you to the determination of the maximum mass of a TOV model. And what remains is the radius. And for the radius, the actual simulation data show again a very nice relationship between the peak frequency at the threshold limit with the radius of the maximum mass TOV star. This is this relation, valid to good accuracy. This is at 2.7 total mass. And so overall now, if you look at these different equations of state, and ask yourself, I know the equation of state, I go through this procedure, can I recover the maximum mass and maximum radius? In some cases you can recover it extremely well, maybe by chance. In other cases the error is large. So what the boxes here show, so we divided practically here those equations of state that go up to 2.2 solar masses, all of them, the worst error, if you look at all of them, in mass is this, and in radius is this. And above 2.2 solar masses, this is the worst error in radius. It's quite large because of that spread in that triangle. But in the mass, it's still around less than 0.2 solar mass, right?
I think it was 1.1.
Yeah, roughly. Okay. And so the final result is that
your errors are all 1 sigma or 2 sigma, or how do you? I mean, just for that.
no, this is a very simple,
Sigma.
a simple determination. It's we have this sample of equations of state, sample of models, and this shows you the maximum error that you have in this sample. And the good news is that after this graph was made, and Andy got additional equations of state that fill this gap here and have also phase transitions, still these maximum error bars did not change. They are still satisfied in this larger sample now. Of course, we would not bet our money that you would never find some exotic equation of state that would have a somewhat larger error bars than what we have here. Okay, this is not the point. But at least for a quite large sample, these are the error bars, and this is, I think, quite useful for distinguishing equations of state. And in the future, we may refine these to give a more precise error bar estimation. And in addition, from the threshold, from the frequency of the m equals 2 peak at the threshold, Andy found that one can also determine to some accuracy what is the central density of the maximum mass model, which I think is useful for equation of state related studies. And I close with a few slides in the last part. I think I'm almost fine with the time.
Yeah,
we started, yes, a bit later.
Interrupted you a lot, so don't worry.
Okay. Now, as I mentioned before, is that we have this numerical waveform, but because of numerical damping, this is damped much faster than one expects because of gravitational wave emission. So one would like to supplement this, to take the first cycle, so the initial amplitude, and let it extend according to a toy model using the actual gravitational wave damping timescale. The question is, we don't know what this is, what is the precise number. And so we have two different estimates, one coming from the empirical relation that Niels and Kokodas found in '98 that gives you the damping timescale of this m equals 2 mode if you know scaled mass and radius. If you apply now this formula to this scaled mass and radius of the actual remnant, then you get a long damping timescale of something like 200 milliseconds. Now, in the meantime, the Tübingen group, Doneva et al., have computed estimates for the damping timescale, frequency and damping timescale, for uniformly rotating stars. And this is a representative result. This is the frequency in the inertial frame for different equations of state. And you can see that as you approach, somewhere here is the mass shedding limit. This is the branch that we're interested in. The rotation splits the L equals 2 frequency into two branches. The lower one becomes unstable when it crosses zero frequency in the inertial frame. This is the CFS instability. And the stable branch is the one that we are interested in. This one seems to flatten out at higher rotation rates in frequency. And if you now plot the same data but in a co-rotating frame, the stable branch comes here, and they found a very nice empirical relation independent of the equation of state. So, which means that the rotational effects on the oscillation frequencies are somehow universal if you are in the right frame to measure them. And in addition to frequencies, they also have this graph for the damping timescale, specifically for this stable m equals 2 mode. And what one sees here, this is the non-rotating limit. These are the highest rotating stars, still uniformly rotating. So you can see that at high rotation, you can reach down to 10% of your initial damping timescale for a non-rotating star. So that the actual, if you want to use these results that are for uniform rotation, the damping timescale would be more like 20 milliseconds. But of course, we know that these remnants are differentially rotating, so the true timescale may lie in between these two, and this is work in progress. Okay. Now, how these hybrid waveforms were used in a data analysis project, you will hear tomorrow from James. Okay. Thank you very much.
Okay, more questions?
I have a question about your last slide.
Mm-hmm.
What do you mean by real gravitational mechanisms? I think you are only considering gravitation and hydrodynamics.
Mm-hmm.
There should be an effect of magnetic field or something like, for example, neutrinos.
Mm-hmm.
What do you mean by real gravitational mechanisms?
Real here means to take into account the actual structure that you have in the remnant, which is caused by differential rotation, and not zero rotation or uniform rotation. So then, of course, one has to consider the time scale in which you can have magnetic braking in the star that could make it, that would change the rotational profile. So there are some estimates for this, and the latest that I could find in the literature, I have not made simulations like that myself, but it seems that it's still highly uncertain, but very rough estimates are on the order of 100 milliseconds for such cases. I don't know, Luciano, do you have something different?
No, I think, yeah, the estimates are extremely crude. They're just, looking at very simple toy models, and they, all of these then says that the damping time is going to be the Alfvén time scale.
Yeah.
But, a lot of nonlinear physics can take place there. If you have an MRI, then this will completely change the standard picture of the differential Rayleigh star. So, I don't think there is any better estimate than one that Nick has written on the slide.
Yes?
What might be relevant is actually the effective number of gravitational wave cycles. Probably James is going to show that tomorrow.
Mm-hmm.
Is that right?
Yeah. Yes?
How robust is your law in section 2 if you include the magnetic field or neutrino emission?
Yeah.
You found that relation between the radius of 1.6 or
Mm-hmm.
frequency, but
Yeah. So the magnetic field could impact in two ways. One is a direct impact on the oscillation frequencies, and this is something that Luciano's group has already looked at, and they found that you need to have extremely high magnetic fields of the order of 10 to 14, 15 to start seeing a difference in the frequency determination. And then an indirect... No, in the merger.
In the spectral.
Yes, yeah. And then an indirect effect is through this magnetic braking that changes the background, which will change the frequencies. But this we have no real estimate on that. It's just back of the envelope for now. It's something, a real challenging problem for the future.
So maybe, Chris, before you, just to as a complement to that answer, if you concentrate on the F1 peak, then that is going to be essentially unchanged by magnetic field. And that's because the F1 is built really at the merger.
Mm-hmm.
And so at that time, magnetic field will not be strong enough
Mm-hmm.
to influence it.
Yeah, I fully agree, yes.
So, Chris.
So
in your mass error budget, are you at all considering the fact that we don't measure mass, we measure redshifted mass?
No.
And that's got initially a sort of, up for advanced LIGO, 5% error on it, you'll overestimate.
Yeah. This is not built in here, no.
It's not as bad as 5%, I think, if you look at it and do some simple analysis.
Mm-hmm.
But I'm wondering if it still adds noticeably to your plot, where you have those regions that look to be about 5%
Yeah.
error.
Well, so far these systems, for advanced LIGO at least, the detectability is, as James will show tomorrow, is in very close distances of something like 15 megaparsecs, 20. So there it will not make a big change. So only with third or fourth generation detectors, if you can go further away, then you will start to worry about the correcting for that. Yes.
By that time, we should know what the equation state is. Then we exploit that for doing other things.
Exactly. Yes.
That's
one less parameter. Yes.
Okay, Kentaro wants to ask a question. This is going to be a bit complicated, but we can try.
Mm-hmm.
Can you hear me?
Yep.
Okay, I have a question in second part. Yep. So you show many equations and complex fitting equations, right? So now started for everything is for one.
Kentaro.
Can you turn off your microphone? Non-linear coupling, that's all. Just turn off your microphone.
Okay.
Wow.
Okay, yes, there are